Hello guys, welcome to the second class of statistical analysis in psychology. Uh, this week we will talk about the visualization and descriptive summary of quantitative variables. In the last lecture we talked about the summarization of the categorical variable, like for the nominal variable. But this week, we will talk about the quantitative variable, the summarization and the visualization of the quantitative variable. By quantitative variable, we are talking about the interval or ratio variable. So in the last week, we talked about the four different types of the variable in terms of the measurement property. You remember that? The nominal, ordinal, interval, and ratio variables. So when I talk about the quantitative variable, that means the scale variable in JESUP, and that is the interval or ratio variable. And in case of the categorical variable, I'm talking about the nominal variable or ordinal variable. So nominal or ordinal variables has the values in different categories. So that's the reason why we call the nominal or ordinal variable as categorical variable. The nominal variable is the categorical variable without any order. The ordinal variable is a categorical variable with some order, right? So an example, you remember that the typical example of categorical variable is the variable sex. So female versus male, and we use an word or a set of letters like the female, FEMALE, to represent the female, and male, the word male, to represent male. So we use a non-numeric characters to represent the categorical variable, the different values in categorical variable. That is a typical situation, and this is pretty natural. But you remember that we can still use the numbers to represent the female versus male. Like, for example, the female, the 1 for female, the 0 for male, something like that. But even though we use the numbers to represent the categorical characteristics or the values in the difference in categories, there is no meaning of the number, right? There's no quantity. So when we say, on the contrary, when you say the quantitative variable, that those variable has the property of quantity. So for example, the interval variable and the ratio variable, they have the values in different quantities. We use the number to represent the differences in interval variable or ratio variable. So the quantitative variable is numeric variable, and typically we treated the quantitative variable as continuous, but sometimes we use a number as discrete. For example, like the integer, like the 1, 2, 3, 4, and 5, something like that. So we can still use the numeric variable as the discrete variable in the quantitative variable. In either cases, in any way, like the quantitative variable can be mathematically operated. For example, we can summing up those values totally and then divide by a certain number. Like we can say that this is a kind of the example of the average calculation, right? When we calculate the average, like we can sum up all the different values and then divide by the number of observations, something like that. So this is kind of the mathematical operation. So the mathematical operation is for the quantitative variable, not for the categorical variable. Okay? So because the categorical variable is not quantitative, it is sometimes or other times or like the called qualitative variable. So the categorical variable and the qualitative variable are pretty much the same thing. But my opinion is like the use of the categorical variable is the better to understand. Okay, so like categorical variable versus quantitative variable. So today we will talk about the what is the best way or the most efficient way of the visualization of the quantitative variable, or what is the descriptive summary statistics for the quantitative variable. That's the main topic of today's class. Okay. And actually, for the categorical variable, we in the last lecture, in the previous week, we have done that for the what is the way of the summarizing the categorical variable in terms of the frequency table, creating the frequency table based on the number of cases for each category, and the calculation of the percentage of the total for each category, and then make a table using those elements. Again, we can still use them to visualize the characteristics of the frequency table using bars or pie chart, something like that. So we can use a bar chart for frequency distribution and pie chart for the frequency distribution, right? Okay, let's go to the different area, like the quantitative variable area. So what is the key features that characterize the distribution of quantitative variable? Let's start with these questions. So here are the main features. Like to understand the characteristics of the quantitative variable, we need to look at these features. The first one is the central location, the typical value of central location in the distribution. And the second important the feature is the spread or dispersion, the extent to which the values in the variable are spread out. So, and the third one is on shape of the distribution, the overall form of the distribution, including symmetry of the distribution and the length of the tails, like the both ends. Those features determine the form of the distribution. So these three are pretty important things to understand the basic foundations of the characteristics. And we can still look at the outliers of the distribution. The outliers are observations that lie far outside the general range of data. Also, we can look at the modality of the distribution, how many peaks are there in the distribution, like just the one peak or the two peaks or the more than two peaks, something like that. So based on these features, we will look at the visualization of the distribution that characterize these features, and we will also look at the statistics or like the numerical summarization of each feature, like for central location or for the amount of the spreadness, something like that. We will look at what kinds of statistics can represent each feature of the distribution for the quantitative variable. And the starting point is the visual investigation. So these features can often be observed visually using the histograms or density plot or box plot, and there are many other plots to visualize the characteristics of these features. And we will look at the numeric values, the statistical measures related with these features. Okay, let's go to the first thing, what are the plots that can visualize these features for the quantitative variable. And the starting point is the histogram. So actually there are many different things, like the plot that describe the distributional characteristics of the quantitative variable. The histogram and the density plot are two most widely used one, the popular one, and these two plots has some provide us some rough idea of the distributional shape of, especially for large size data. These are pretty much the like the summarization of the distribution with a simple format. And we will look at the other types of the visualization, like the stem and leaf plot or dot plot, mainly for the small size data. And those two plots give us the detailed and complete description of the whole values in the distribution. And there are other types of the plots still, like the box plot, the violin plot, or rain cloud plot. We will look at those plots too, but not all today. So let's go to the next step. I will use the same data set, the sleep data set from the first week, the illustration. You remember that in the sleep data set, we have the extra hours of sleeping after taking a sleeping pill. And we remember that there are 20 observations. So let's look at this. This is the data file, right? So the extra variable in the sleeping data set was the hours, extra hours of sleeping, right? 0.7 means like the first participant slept 0.7 hours more than the control thing, right? And minus 1.6, like the sleeping hours has been decreased 1.6 hours, something like that, right? So we don't have missing values in the extra variable. So look at the distribution plot, beginning with the histogram. So first impression of the characteristics of the distribution often comes from drawing a histogram. So in most cases, histogram is the starting point to understand what is the characteristics of the distribution in terms of the visualization. And histogram is based on splitting the data into frequency bins. Like the histogram is pretty much the same as the bar plot for the frequency table for like categorical variable. So remember that in the categorical variable, to create the frequency table, we need to count the number of observations for each category. But in case of the quantitative variable, because we don't have the categories, we have to create the category like the interval bins across the range of the variable. So for this case, we have like the hours, right? And like the extra hours, we need to create the bins. And in this example, we create the 8 different bins from the -2 to -1 for the first bin, and the second one is a -1 to 0 hours, extra hours, right? And for each interval bins, we need to count the number of observations. For the first bin, we have the 2 observations, and for the second bin, we have 4 observations. And in this case, the sum of the total bins have to cover the whole range of the value. So starting from the -2 up to positive number 6, this this range should cover all the values in the data set, right? And there is no overlap in the interval bin. It shouldn't be there. Okay, so that means it is exclusive. The bins are exclusive to each other, and they combined in terms of the combination of the total whole bins. It is comprehensive, Okay, and we still can calculate the percentage of each category, like each interval bin. And after we create this table, like the frequency table, like these things, we are ready for the diagram, the plotting, the histogram. Okay, and this is the plot of the histogram. And we see we have then 8 interval bins, and actually we have 7 bars, and with no gaps between the bars. So this is the main difference between the histogram and the bar graph of the frequency table. And like the histogram has no gaps between the bars to represent the continuous characteristics of the quantitative variable, right? And we see the x-axis and y-axis and the rectangular shape of the bars. So let's look at each element. The x-axis represents the range of values of the variable, like from -2 to 6, and divided into intervals called bins. So we have 8 bins, right? And the y-axis represent the frequency or count of data points, like we have the 2 observations in the first bin and 4 observations in the second bin, something like that, falling within each bin. And rectangles are drawn for each bin with the height proportional to the frequency, right? Okay, and there are different ways to determine the number of bins and the width of the bins. So if we have the different number or different width of the bins, the shape of the distribution, the height of the rectangular, they are different. So because there are different ways to determine the number of bins and the width of the bins to create the histogram, the shape of the histogram may differ significantly depending on the number of bins and the binning method. Okay, so that is the one weakness of the histogram. But in most cases, most computer software, the program automatically provide us the reasonable shape of the histogram in most cases. So that's not a critical things. And let's look at the other types of the plot, like the stem and leaf plot first. In the stem and leaf plot, as I explained before, the stem and leaf plot and the dot plot, they represent each element, each value in the distribution comprehensively, but in different ways. In the stem and leaf plot, all values are expressed completely. Like for example, if we have the 2 columns in the stem and leaf plot, with the stem column and the leaf column, and each leaf has each observation or each value. So we have 2 values in the first row, 2 observations, and the 3 values, 3 observations in the second row, and so on. So totally we have 20 leaves because we have 20 observations. And how can we read the value in the stem and leaf function? The stem part is the first digit, and the leaf part is the first digit after the stem. What does that mean? Before we interpret the number, we need to figure out what the vertical bar between the 2 columns represent. Vertical bar between the 2 columns represent the decimal point. In this case, the decimal point is at exactly at the vertical bar. That means minus the leaf of of 6, the value 6 in the leaf and the minus 1 in the stem represent minus 1.6. And the leaf 2 in the first row represent minus 1.2. So we have 1 minus 1.6 value in the extra hours variable here, right? Minus 1.6. There is no other the minus 1.6 in the variable. And we also have the minus 1.2, just a single minus 1.2 value here. We see here, just like that. And for the next one, let's look at the third row. We have on the stem of 0 and the leaf of the 0, 1, 7, 8, 8. So we have 0.0, the single value, that means 0. And we see the row 9, the value 0. And 1 represents 0.1. And where is it? 0.1 here, the single one. And 7, a single 7, and the double, the 2 of the 8, 8, 0.8. So 0.8 here and there, and 0.7 just 1. Okay? This is the way to read the stem and leaf table. Okay? And dot plot also represent whole number of observations. So we have 20 dots here because each dot represents each value, each observation. But we don't have the specific value. It just has a dot. Okay? So it's pretty similar to the stem and leaf function, but without the detailed information in leaf area, right? So the dot plot displays the distribution where each dot represents a value. If a value occurs more than once, the dots are placed one above the other, just like this, so that the height of the column, like this one, represent the frequency for that value. So we have 4 observations near this area, right? So because of this, dot plot give us some sense of the distributional shape. So these are the more concentrated area with many observations, and this area or this area is we don't have many observations here. So we see the shape of the distribution by looking at the dot plot or the stem and leaf plot. Okay, they're the same. This is the same like for the stem and leaf plot. So we see some kinds of the shape of the form of the distribution by looking at the stem and leaf plot or stem and leaf table. Just like when we look at the histogram, right? Okay, let's go to the next part, the density plot. The density plot is a variation of a histogram that uses corner smoothing to plot values, allowing for smoother distributions by smoothing out the noise. So this is the density plot, shape of the density plot. We see the curve instead of the rectangular. So the form of the distribution is smoothed by corner smoothing. This is a kind of the smoothing procedures. We don't have to understand what exactly is going on in the corner smoothing. We just need to understand that, oh, this is a kind of smoothed, more like the curvy shaped distributional visualization. The peaks of a density plot help display where values are concentrated over the interval. So in this case, we see that these area are the peak area, right? So we say that, I guess that there are many observations here, right? And we already know that this area has a lot of observations, right? This area. So the advantage of the density plot is over the histogram is that they are better at determining the distribution shape because they are not affected by the number of bins used. So in the histogram, the shape of the distribution depends on the method of the binning, so number of bins, something like that. But in the density plot, we don't have to create the bins, so we don't have to decide the number of bins, we don't have to decide the width of the bins. It is automatically like the calculated by the smoothed values like this. So there is just a single solution of the distributional shape when we use a density plot. We can use different ways to like to change the shape in the density plot, but the default setting or the most widely used method of the corner smoothing density plot is that produce like the single, the converged solution of the output. That means it gives us always the same answer. So this is a great way to investigating the characteristics of the distribution for a quantitative variable. Okay, let's look at the first one, the measurement of measures of central tendency. The central tendency is the central location. Like the central tendency of a variable refers to a single value that aims to describe the center or typical value of a data set. It is essentially a way to summarize or represent the entire set of data with one number that best captures the middle or most typical value. So you know what it means. Like there are, let's look at each of the central tendency. There are three main measures of central tendency: mean, median, and mode. The mean is the arithmetic average of all values in the data set. We know that. The median is the middle value when the data is ordered from least to greatest. So it's in the middle in terms of the amount of the numbers, amount of the values. And the mode is the most frequently occurring value in the data set. We know the model in terms of the categorical variable, like the category with the most frequent number of observations. That is the order, the mode. That is the mode of the categorical variable. But we can still apply to the mode, the concept of mode for the quantitative variable. If we use the kinds of the interval bins, something like that. So the mean and median, like for the quantitative variable, the mean and median, they are most widely used, the central tendency. And each of these measures provides a different perspective on what's central or typical in a data set. So the definition or the perspective of what is central or what is typical, according to that kinds of differences, we may use on different types of the central tendency. For example, for the mean takes into account every value, like because we summarized all the values when we calculate the mean. So that is a good thing. So the mean has all the information from the values or the observations. There's no the missing value in the calculation of the mean. So that's the good thing for the representative value, right? But it can be influenced a lot by outliers, like the most non-typical values. Non-typical values can affect a lot in the calculation of the mean. So that's a weakness. That's a bad thing. So the mean has a good property as well as the bad property. Mean is also a centroid in geometry. Like the centroid means like the center of mass. So like if we have an extremely large or extremely small value in our data set, it affects the location of the center of mass a lot. But in case of the median is less affected by extreme values, and because of that, median is useful for like the distribution with extreme values or non-typical values, or the distribution with skewed shape. What is the skewed shape? The skewed shape is an asymmetric, like the long-tailed shape. That is a skewed shape. So in case of that kinds of characteristics, the median has a good property for the typical value or the middle value than the mean. The mode is typically particularly useful for categorical data, as I said before, or when you want to know the most common value in a quantitative variable. But it is like the pretty challenging to get a mode from the continuous, especially for continuous quantitative variable. Okay, so remember that the mean and the median are most widely used central tendency for the quantitative variable. And you may know that how can we calculate the mean? The mean is calculated as the summation of the whole numbers, whole values, and then divided by the number of observations. And it will give us the mean value, right? And for the median is selected as either in case of the odd number of observations or in case of the even number of observations. In case of the odd number of observations, like for example, n is equal 5, then we can use the 5 plus 1 is 6 and divided by 2 is 3. That means the third value is the median. So you have some sense, right? If we have 5 different values in our data set, the third one is the middle one in terms of the order of the location, right? If we have 3 observations, 3 plus 1 divided by 2, the second value is the median, right? Does it make sense? But in case of the even number of observations, for example, let's say that we have 4 observations, so there's no the middle value among the 4 values, because we have a second value and the third value, and so the average of the second value and the third value in this case is the median. That is the median. So average of the two the central location values give us the median. Okay. And the choice of which measure, like from the mean, median, and mode, to use depends on the nature of your data. Like in case of the categorical data, we have to use a mode instead of the mean and median. But in case of the quantitative variable, in most cases, we use a mean or median instead of the mode. And the specific questions you are trying to answer. So if your questions is about in the middle in terms of the location or the order, you are like, you want to use a median instead of the mean, something like that. So it depends on the question and answer, the types of the question and answer. Okay, sometimes it's valuable to look at all 3 to get a comprehensive understanding of the data set's central tendency. Based on this understanding, let's look at examples to understand in more detail about the characteristics of the mean and the median, the central tendency. First data set has 6 observations from like the 89, 74, 91, 88, 72, and 84, something like that. So 5 values in the data set B is exactly, they are exactly same as in the data set A, and just only one value are different. The 72 for the first set, the set A, the 54, 72 versus 54 for the set B. Okay, let's look at the dot plot for the first data set. This is the dot plot, so 6 dots in here, and we see the diamond shape here, the red colored diamond, and that represent the mean. The mean of the 6 values are 83 in this case. And the green one, because we have an even number of observations, the third one and the fourth one and the average of the two values are the median. So the number 86 is the median. That is the average of these two numbers, two values. So let's look at the next set that has the difference only in the first one, the lowest value. Like this is the 72, I guess, right? And now the second, in the set B, there's the value 54 instead of the 72, and this is the set B, the dot plot for the set B. So now we have 54 instead of 72, right? So now we have a pretty lower value, atypical value, and because of this non-typical smallest value, the mean changed a lot, like from 83 to 80. It decreases by 3, right? But in case of the median, there's no change at all, because the median is calculate the average of the middle point 2. The 2 points, 2 values in the middle, they don't change at all. So because of that, this non-typical value, the lowest value, doesn't affect the calculation of the median, but it affects the calculation of the mean a lot. So that's the main difference between the mean and the median. Okay. And in terms of the mode, all values are unique, so there's no mode defined. Okay, let's go to another example, another variable that is generated by the computer and have the number of observations 41. Okay, so we have 41 observations in this data set. And now this is the histogram of the 41 data, the variable, the 41 values. So we see the mean and the median of the distribution. It's shaped like the pretty skewed, like the unbalanced shape of the distribution. And we see the histogram of the distribution, and the curve is the density plot. So you have some sense about what is the relations between the histogram and the density plot. The density plot has less noise and it is smoother than the histogram, something like that. So each line represents each observation. So we have like 41 lines here, the log, the marker here, and because we know that when we have 41 observations, the median is the 21st observations when it's sorted by the amount, right? So here is the median, like the green line. This is the median. So that means this is the 21st the order of the value. So we have 20 values below the median, and we have 20 values above the median, right? And because we have like the far away values from the median on the right hand side, the mean has changed towards the atypical extreme values, right? So when we have on these types of the skewed distribution, the value mean tend to move towards the atypical, the extreme values. So that's the reason why we have the greater mean than the median in this distribution. Okay. We have looked at the three different central tendency measures. Now we need to look at the other types of measures of locations instead of the measure of central location. And before we go to the next part, there is some explanations why the mean and median and mode called central tendency instead of the central location. So if you are interested in this topic or this question, just to read through this part, we don't have enough time to for the additional explanation of this part. So let's go to the next part. Okay, let's talk about the quartiles and the measure of other locations. And think about the median. Median is the cut point that divides the data into two equal size groups when the data is ordered from smallest to largest, right? So median is the 50-50, the cut point for the 50-50 division. Similarly, we have like the median type of location informations. And the most general type of the location information is quantiles. Quantile is translated as in Korean like the 분위수. And quantile is on relative locations in order from smallest to largest in the unit of 0 to 1. Okay, so the 0.5 quantile is the median, because this is in the 0.5 quantile, and below that quantile we have on 0.5 portion of the data, and above the quantile, like 0.5 quantile, we have the 0.5 portion of the data. So that is the exactly same definition of the median, right? And in many cases, because in the quantile, the unit of the quantile is 0 to 1, like the 0.9 or 0.1, something like that, it is not widely used. Instead, the other types of quantiles are more frequently used, and the frequently used quantiles are quartiles and percentiles. And these are the two most widely used types of quantiles. Quartiles is translated as an 4분위수, 4등분, 4분위수. And quartiles are the three cut points that divide the data into 4 equal size groups. Or the quarters. The quarters, each quarters has 1/4, like 1/4 size of the total for each group. Okay, so we have the first quartile, the second quartile, and the third quartile, and Q1, Q2, Q3 are used to represent the first, second, and the third quartiles respectively. The first quartile, Q1, is the cut point that lies between the first quarter and the remaining 3 quarters. Okay, the second quartile, the Q2, is the cut point that splits the first half and the other half. The first half is the first 2 quarters, and the other half is the last 2 quarters. And that is the median, right? So the second quartile is same as the median. And this is the same as on 0.5 quantile, right? And for the Q1, what is the Q1 equivalent quantile? That is on 0.25 quantile, right? Okay, and for the third quartile, the Q3, that is the cut point that lies between the first 3 quarters and the last quarter. Okay. And what about the percentiles? When we talk about the percentiles, we imagine that we have 100 chunk equal sized groups of the variables, groups of values. Okay, so a kth percentile is a score below which a given percentage k of scores in its frequency distribution falls. For example, the 90th percentile is a score below which 90% of scores in its frequency distribution falls. So we have 90% of the scores of the total distribution is below the point, the 90th percentile point. Okay, only 10% of the total scores are like exist in the above the 90th percentile. Because of these types of characteristics, the 3 quartiles, the first, second, and the third quartiles, the 4분위, 4등분 quartiles, are the 25th percentiles and 50th percentile and the 75th percentiles of the data point. They are same. The Q1 is the 25th percentile, the Q2, the median, is the 50th percentile, and the Q3 is the 75th percentile of the data point. So this isn't just a dot plot for the same data set. And look at here, like because we have the 41 observations, and this is the 21st observations in order. We have 20 observations below this point and 20 observations above this point. So this is the median point, and the second quartile point and the 5th percentile point, and that is the value of the 7.04, the median. And for example, what about the first quartile? And we have 10 values below this quartile, the first quartile, and the 30 values above the quartile, the first quartile, right? So 10 versus 30. So that's the main point of the first quarter versus the remaining 3 quarters. This is the location that split the first quarter and the remaining 3 quarters. Okay, and what about the third quarter? And this quarter, like below this quarter, the third quarter, we have 30 observations, and like this one, the above this observation, we have the third quarter, we have the 10 observations in this distribution. So that's the reason why we have the third quarter in the 41 observations, number of observations, right? So and the third quarter is 11.52 and the first quarter is 4.34. And here we see the IQR, and that is on 7.18. What does IQR represent? So this is an interquartile range. This is a kind of the range. Range is the difference between the minimum value and the maximum value. But the interquartile range is within the range, in the middle. The range of the middle, that is the difference between the third quartile and the first quartile. The third quartile and the first quartile, right? This is the range, interquartile range. So you see the 11.52 the distance between these two values is the 7.18. So the number 11.52 minus 4.34 will give us the 7.18, and this is the length of the between the two quartiles, and it gives us some sense about how much the values in the distribution are spread out, right? And this is one way to represent the amount or the extent of the dispersion within the distribution. The quartile information, the location of the quartile, the three quartiles with the maximum and minimum value, it will give us like the very like useful information about the characteristics of the distribution, like the dispersion, the central location, and the shape of the distribution, something like that. And based on these five numbers, like the minimum value and maximum value and three quartiles, we can plot kinds of the characteristics. We can represent the characteristics of the distribution with these five numbers, and that's the way we draw the box plot based on these five values. And it is one of the most useful distributional plot among all the types of the distributional plots. So let's look at the box plot and see what happens. The box plot or the box and whisk plot is some kinds of the visual summarization of data distribution using 5 key points. As I said before, the minimum, first quartile, median, the third quartile, and the maximum. The box plot uses just these 5 numbers. The maximum value is used for the bottom of the lower whisker, and the first and the third quarter is the bottom and the top of the box, and the median is the line in the box, and the maximum value is the top of the upper whisker. So let's look at this box plot here. So we have 5 values represented by this plot. So we have the box in the middle, and this is the first and the third quartile, and this line, the thick line, represent the median, the second quartile, and this is the minimum and the maximum value. So these 5 values are used to draw the box plot, and this plot gives us some broad sense of the characteristics of the distribution. And this is the same for the right hand side. And we have the box plot here, and these are whiskers. So whiskers, and these are outside of this area, the most observations distributed area. And we call this kinds of like the atypical, non-typical value, and sometimes we call this is a outlier from this distribution. The box plot shows the central tendency, the median, as the line in the box, and it also shows us the spread, the size of the box, the amount of the extent of the spread by the size of the box, the overall range, and it is robust to outliers. As we have seen before, like the location of the first quartile and the third quartile is not affected by the extreme non-typical values. That is the outliers. So that means the spread is robust to the outliers. And it also shows us the symmetry of the distribution because the box can be asymmetrical, or the whiskers can be asymmetrical, and that represent the unbalancedness or non-symmetry of the distribution. And the fourth one, the potential outlier. Box plot also shows us potential outliers. the outliers are points beyond the whiskers, and often plotted individually. So as we have seen before, in this case, this is the way to represent the outliers in the box plot. Okay, so this is outside of the box and whiskers. It's far from the whisker end. Okay, so how can we determine the length of the whisker when we have potential outliers? The whiskers, originally whiskers is the end of the whisker is the minimum value and the maximum value, but when we have potential outliers, whiskers extends from the box to show the rest of the distribution from the box, like from here, like this one and this one. But also whisker typically extends to the lowest and highest points within 1.5 times the IQR from the edges of the box. So IQR is the interquartile range, you know that, and that is represented by the size of the box, right? Size of the box, like the Q3 minus Q1, that is the amount of the spread, and that is exactly what IQR means. And 1.5 times the IQR is the determining factor of the outliers from the lowest and highest point, highest and lowest edge of the box, right? So from this, like for example, like in case of the left side distribution, we see that the maximum value are here, and we have the size of the IQR is this amount, and from this edge, 1.5 times this amount is like this amount, right? And all the values, including the maximum values, are existed within this area, this boundary, and that is true for the smallest values here, right? The minimum values are within the boundary of the 1.5 times this IQR distance, like this one, okay? Like this amount. The minimum value is within that area. But in case of the right-hand side, this is the IQR, size of the IQR, and 1.5 times 1.5 times IQR is about this amount, right? And this value is outside that boundary. So that's the reason we call this as outlier. Okay? And except this one, the maximum value of the remaining observations are this amount. And this value is within the range of the 1.5 times the IQR from this edge. Okay? So we only have one outlier in this case. So box plot is used for the comparison of the distributions across groups or multiple variables side by side. This is a pretty simple type of the distributional plot, and we can use the simple box plots to compare the many different distributions, like across groups or across variables, something like that, side by side. Okay, this is a pretty useful method of the comparison of the different types of variables. And the second usage is on identifying the outliers. So we have different types of the definitions of outliers, but one most wide useful definition is based on the box plot or the IQR range. So 1.5 times the IQR from the edge of the box is the most widely used definition of the outliers. And we can also assess the data symmetry by just looking at the shape of the box plot with whiskers. But it is like the rough approximations. This is not a comprehensive or the detailed description, but it's just an efficient and useful summary. And box plot summarizes large data sets efficiently, just as explained before. When we have many variables and many occasions, it is very the simple way to investigate their distributional characteristics. So in summary, the advantages of the box plots are compact approach and easy to compare, and it shows key statistics clearly. But for the limitation of the box plot is a box plot doesn't show full distributional shape. For example, it doesn't give us some bimodality. Like if there is two peaks in the distribution, the box plot never provide us that idea to us. Okay, let's look at the example in more detail. Like when we look at the distributional statistics, descriptive statistics related with the box plot, we see the median value here for the two variables. The one is for extra hours, and the other one is generated by computer. The 20 observations are generated on purpose for having some skewness, positive skewness in the data set. So the median value is 0.95 and 2.5, about 2.5, and mean value is this one. And because these are intentionally generated for having the positive skew, the mean value is toward the larger values, right, from the median. But this is the same for the extra hours variable. And the IQR is on this amount, and for the second variable is on 2.65 something. And the range, the difference between the minimum and maximum value, like the 5.5 minus 1.6 will give us 7.1. And the distance between the two values are 14. Okay, and let's look at the first quartile, the second quartile, and third quartile. For the extra hours variable is the first, second, and third quartiles are minus 0.025 to 3.4, like this. And these values are exactly represented here in the box. First, second, and third quartile, right? And for the pos skew variable, we also have the first, second, and third quartiles from 0.9 to the 3.6. Here, 0.9 to 3.6. Okay, so the histograms. So we use on these 5 numbers. In case of the first variable, extra hours, we just use on these 5 numbers. And for the second variable, because we have an outlier in this case, we have this number and the remaining 3 quartiles. But this one should go to here, right? And then we don't have the maximum value except this value. So we cannot decide what is the end of the upper whisker from this table. Measures of dispersion for a quantitative variable describe how spread out or scattered the data points are. These measures help us understand the variability in a data set. The main measures of dispersion include the range, variance, standard deviation, interquartile range, and median absolute deviation, and coefficient of variation. We introduced the 6 different measures of dispersion. The range is the difference between the maximum and the minimum values. It is simple, but the most sensitive to outliers, right? So extreme value influence a lot, like in range, the most sensitive one. The variance is the average of squared deviations from the mean. So the function for the calculation of the variance is the squared deviation. Deviation means like each observation, distance between each observation and the mean, from the mean. So observation minus the mean. And the squared deviation means the square of that deviation. And the summation of all the squared deviation. Like if we have 20 observations, we have 20 dispersion deviations from the mean, and we have 20 squared deviation from the mean. So let's summing up the 20 values, the squared deviations, and then divide by the number of observations minus 1 over 1. Okay? So just divide by the n minus 1. And n minus 1 in the denominator should be n in population to represent the average of the squared deviations from the mean. But in most cases, we are dealing with the sample instead of the population. We will talk about this topic later when we talk about the population and the sample, the distribution, the difference between the two, and what is the inference from the sample to the population, something like that. We will talk this later. So for now, the most widely used formula for the calculation of the variance is just this one, so n minus 1 in the denominator. But in case of the population, it should be n instead of the n minus 1. The variance is useful for further statistical calculations. So like we can say that the absolute value of the deviation. So absolute deviation is the more straightforward to understand, easy to understand. But why do we need to use the squared deviations instead of the absolute value of the deviation? The main reason, there are many reasons, but the main reason of the use of variance instead of the absolute value of the deviation is it's useful in terms of some mathematical properties, so statistical calculations. Okay, I will not explain this in more detail, but just like that. And variance is more sensitive to outliers than IQR and MED. IQR and MED are based on the median and the quartiles and the absolute deviations from the median, something like that. So IQR and the MAD, the median absolute deviation from the median, these also are the measure of dispersion, and those measures of dispersions are based on the median, and they go along with the median. Okay, but for the variance and the standard deviation, that is the calculation from the mean, this deviation from the mean. So variance and the standard deviation go along with the mean. Okay, so standard deviation is the square root of the variance, because square root the variance, the unit of the variance is squared. It doesn't match the unit of the original variable. So that's the reason why we square root of the variance to match the unit of the variable. So standard deviation are the most commonly used measures in the same unit as the original data. And just like the variance, standard deviation is sensitive to outliers than the IQR and MED. And now, what is the IQR and MED? IQR, I already explained it. The difference between the third quartile and the first quartile. or the 75th percentile and the 25th percentile. And it go along with the median, as I explained before. And these are the IQR is less sensitive to outliers. That is the robust measure of dispersion to outliers. And just like that, MAD, the median absolute deviation from the median, so MAD, or sometimes the mean absolute deviation of the median, the MAD is like this one. And it's a one way of the calculation of the measure of dispersion. And it is less commonly used, but interpretation is straightforward. And just like the IQR, the MAD is less sensitive to outliers. So that is these kinds of the robust measure of the dispersion to outliers. And there are another measure of the dispersion called the coefficient of variation. And this one is just a standard deviation divided by the mean. So measures of dispersion scaled by the mean is the coefficient of variation. And in psychology, the CV is not widely used. It is widely used in like the economics or like the market sharing, something like that. And it is useful for comparing dispersion between data sets with different units of or means. Let's talk about the shape of distribution. Shape of distribution describes the overall form of the distribution, including symmetry or the asymmetry, or sometimes the skewness. All those three things are the same, like the opposite sides of the same coin, something like that. The symmetry is the whether the data are mirrored around the center. So it's like the flipped image of the other half, right? And the skewness is the degree of asymmetry. The right skewed is positively skewed. Left skewed is negatively skewed. Like the positively skewed has a number, the skew value, positive value of the skew, and negatively skewed, the negative value of the skew. Left skewed, like the tail in the smallest value. And the right skewed distribution, tail is in the largest value. Okay, and the kurtosis and actually the skewness of 0 represent the symmetry, the perfect symmetry of the two distribution of the one single distribution with for a quantitative variable. And the kurtosis describes the tailedness, or how heavy or light the tails of the distribution compared to a normal distribution. So the normal distribution is the reference distribution for the calculation of the kurtosis. But we don't have the normal distribution yet. We don't have any sense about the normal distribution yet. So we will discuss this topic later. But just to remember that in terms of the heaviness of the tail or length of the tail, the reference is the normal distribution. If a distribution has the longer tail than the normal distribution, we say that that distribution has a longer tail, a heavier tail. And in that case, we call that distribution is leptocrutic. Leptocrutic means with the long tail. And if the distribution has a shorter tail or the right tail than the normal distribution, we call it a platycrutic. And another the element of the shape of the distribution is modality of the distribution. The modality is the number of the peaks. So when we have a one peak of the distribution, we say that distribution is unimodal. And if we have two peaks, we call it a bimodal. And if we have multiple peaks, more than 2 peaks, we call the distribution is multimodal. So, and this is an example. Like we have 3 different values. One is the original, the extra hours variable, and the other one is on the right skewed, like positive skewed variable generated from the computer. And the next skew variable is on just a mirror image of the pos skew variable. So it is exactly the same, the mirror image of the other variable. Because of that, these two variables have the same amount of the dispersion, standard deviation, and coefficient of variation. Oh, no. This is not the same between the two because it is scaled by the mean. We have the different means in here. So forget about this. So for the MAD, variance, and standard deviation, they are all the same for these two, across these two variables. And for skewness and kurtosis, and forget about the standard error part. We don't use this part anymore. Like just look at the skewness and kurtosis, because these are just a mirror image of the of each other. They have the same amount of the kurtosis, like the length of the tail, but the direction of the tailness or skew is just an opposite, but the degree is the same. The direction is opposite, right? And for the extra hours variable, it has the small size of the skewness and small size of the kurtosis. Okay, and when we see the histogram and the density plot overlaid with each other with the log values at the bottom, this is the plot, distributional plot for the three variables. And we see the original variable, the extra hours variable, is like not that skewed, or the with high level of kurtosis or lower level of kurtosis, something like that. It is rather like the lower level of kurtosis. Kurtosis of 0 means that the tailedness is about the same as the normal distribution. So in this case, we have a negative value in terms of the kurtosis. It has the shorter tail than the normal distribution. Okay, and for the other two variables, just the mirror image of each other, it has a pretty skewed shape, and it also has a pretty long tail. The kurtosis of the two variables are pretty high, right? We see that. And the positive skew for the pos skew variable, like this way, the right skewed, the higher number of the outliers, and the negative value of the skew represent the lower value of the outliers, and the left hand side tailed skew distribution. And when we look at the box plot with the violin shape, this is a violin plot. Violin plot is just an look at this. These are three variables, the box plot with the violin plot. See here, what is this shape? Where this shape from? Looks like the violin, but how can we draw this line based on what? And it is actually from this kinds of the density plot. You see here the density plot, and this is the just like the density plot from this to this. Okay, so and for the skewed variable, we see the very skewed part of the shape of the box plot as well as the violin plot. So what is the violin plot? Violin plots are similar to box plots, but provide more detailed information about the data distribution. The key features of the violin plot is the shape, width, and the inner markings. The shape is the rotated kernel density plot on both sides. We have both sides a mirror image of the density plot, right? From this one, and from these two, we have this Bioline plot and that Bioline plot. Okay, so the shape is the rotated kernel density plot on both sides. Okay, and the width of the Bioline here represent the frequency of each point, frequency at each point, and the inner markings like often include median and quartiles like the box plot itself. The median and the quartiles like this one, the box. Okay, the Bioline plot often include these median and quartiles. The Bioline plot shows the full distributional shape and central tendency and spread, peaks. The modality can be shown from the Bioline plot, but not from the box plot. You remember that. And the symmetry or skewness, we can see the symmetry or non-symmetry of the plot using the Bioline plot. And what is the advantage of the Bioline plot? So Bioline plot is more informative than box plot for complex distributions. See, right? And Bioline plot reveals multimodal data. So when we have multimode in our distribution, box plot cannot give us the multimode, right? But a Bioline plot can do. And a Bioline plot shows probability density, right? This is the probability density. The kernel smoothing plot is on the probability density. But what is the limitations? A Bioline plot can be harder to read precise values, and Bioline plot may be less familiar to some audiences. But in spite of those kinds of the limitations, we use the Bioline plot for these purposes. The first one is comparing distributions across groups, just like the box plots, and visualizing complex data patterns over the box plots, and identifying out clusters or subgroups within data, like the modality, the multimodality. So, in conclusion, the Bioline plots are particularly useful when you need to see the full shape of the distribution, especially for multimodal data or when comparing multiple groups. So that's the usage of the Bioline plot. Okay. We spent a lot of time for today's lecture, and this is the end of the lecture. Thank you. Goodbye.